So, in this lecture we shall be working out another example. See, working with examples is good in two respects. One is that it can give you confidence in actually learning about the language and how you can approach the design of a thing, and secondly you can actually understand the flow, the design flow, how it is actually done in practice. So, the second example that we will be taking is a slightly more complex example than the multiplexer we took last time. This is the example of an adder, and means an adder circuit which is part of an arithmetic logic unit, ALU. So, this is our lecture topic. So, we describe an adder. Again we start with the behavioral description of an adder. Now, let us see that what we are trying to do here. Now, this adder is just symbolic as an example we have taken, but in general let us call it this is an arithmetic and logic unit, but in the code that I will show we will only talk about addition. So, what does the ALU do? The ALU will take two data as input, let us call them x and y, and it will be generating a result, let us call them as z as output. So, the example that I will be illustrating, I shall be only talking about addition. And in the structure of course, we will be elaborating, and addition we shall be looking at one more thing. What? We shall be looking at the process of generation of the status flags. See, in many processors, you may be aware of, there are some status flags which are automatically set as a result of some arithmetic or logic operations. So, the status flags that we shall be looking at are sign, 0, carry, parity and overflow. These status flags actually will give us some idea regarding the addition operation that have been taken place. The sign flag will tell whether the result is negative or positive. The 0 flag will tell whether the result is 0 or non-zero. The carry flag will tell whether there was a carry out of the addition. The parity flag will tell whether the number of ones in the result is odd or even, and overflow will tell that well the result means after addition I have done something which is not fitting, there is an overflow. So, whether there is an overflow or not. Okay. So, we shall be looking at the design of an adder with the generation of these 5 status flags. Okay. So, we start with the version 1 of our design, which is the behavioral description of the adder. So, this 5 status flag I have already mentioned. Okay. Fine. Let us straight away look into the design. This is our behavioral design of our ALU or the adder. You see what are the parameters? The name of the module you have given as ALU, x, y, z, x and y are the inputs. Let us assume they are 16-bit numbers 0 to 15, z is the output, and these are the 5 flags sign, 0, carry, parity and overflow. These are all outputs. Now, the addition operation I am doing using a behavioral fashion, using the single statement, assign, carry and z using the concatenation operation, because z will be the result and the carry out of the addition that will go into the carry flag, right, that is the carry. So, I am generating carry right away like this, carry and z, this will be 16 plus 1 17 bits equal to x plus y. Now, the other status flags, how are they generated? Well, sign, well, numbers are represented in 2's complement form typically. Now, in 2's complement representation, the most significant bit of the number indicates the sign. If it is 1, it is negative, if it is 0, it is positive. So, the MSB of the result z, that will go into the sign flag straight away. So, we are straight away assigning z 15 to sign, the most significant bit. 0 flag, what is 0 flag? 0 flag will tell whether the result is 0 or not, which means z, the 16 bit sum, it is 0 or not. 0 means all the bits are 0. If it is 0, this 0 flag will be set, it will be 1. So, what kind of operation do we require? If all the bits of z are 0, I have to set z flag to 1, 0 flag to 1. So, I need a NOR operation. I take OR of all the zeros. If the inputs are all 0, output of OR will be 1, then a NOT, it will be, the OR will be 0, then NOT, it will be 1. So, NOR will be 1. Okay. So, I need a reduction operator NOR, just I write assign 0 equal to reduction NOR on z, that will be 0. And parity is just exclusive NOR. If it is even parity, it will be 1, if it is odd parity, it is 1, it is 0. So, we simply write assign parity equal to again reduction operator exclusive NOR of z. So, generation of sign 0 and parity are very simple. Okay. Now, overflow, there are various ways to detect overflow. The way we are implementing overflow is like this. Let us say we have a number x and y. This is our bit number 15, our most significant bit, and this is the sum z. So, here also we have bit number 15. Now, here we are saying that there will be overflow if the condition that has to be followed is this. I am just writing down, then I am explaining. This means that either both x 15 and y 15 were 1 and 1, this is dot means AND operation, plus means OR operation, x 15, y 15, z 15 bar, which means this is 1 and this is 0. So, the numbers were negative, after addition the number has become positive, which is never possible. This is possible only when overflow has taken place, or the reverse condition, this was 0, this was 0, but in this sum it has become 1. The numbers are positive, but this sum is showing as negative. So, if you implement this logic, that will give you the overflow straight away, right. So, here we have done exactly that, we have used this same expression to generate the overflow, right. So, this is the behavioral description of the adder. Now, just like in the example we showed earlier, we have also written a test bench here. So, we call it as ALU test. So, we have instantiated this module called ALU, this is the module ALU. So, we have given this name DOT, the parameters are given. So, again in the initial block we have given dump file, dump variables, we have monitored the time, XYZ and all these status flags. Okay. So, here we have instantiated the status flag names we have given as S, 0, ZR, CY, P and V. In the same order we have given the variable names, same order. Okay. So, these names we can change, same names are not required. Okay. And the input data that we have applied are, you can see with delay of 555 we have given. In the first step we have given the first number x equal to 16 bit hexadecimal 8 FFF and 8000. So, let us just note down these numbers. At time 5 we have applied x equal to 8 FFF and y equal to 8000. Then again after a delay of 5 we are applying x equal to FFFE and y equal to 0002. So, after delay of 5 means at time 10 we are applying x equal to FFFE, y equal to 0002, and again after delay of 5 we are applying x is AAAA and y is 5555. So, at time 15 x is AAAA, y is 555 and 5, right. So, let us see just by normal addition what will be the sum. If I just add 8 FFF and x and y equal to 8000, z will be f and 0 is f, f and 0 is f, f and 0 is f, and 8 and 8 will be 0 and there will be a carry out. And here E and 2 if you add it will be 0, there will be a carry. So, 1 and f will be 0, carry, 1 and f will be 0, carry, 1 and f will be 0, it will be all 0 and there will be a carry out again. And here A, if we add A and 5 is f, B, C, D, E, F. So, F, 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 right. So, this should be the sum and of course, the flags will be set. Let us see. So, if you just simulate, the simulation output is showing this. At time 5, 0 FFF, 0000, FFFF. So, this is exactly what we got here, 0 FFF, 0000, FFFF, and in the all cases you can verify the sign 0 FFF, the sign is positive, 0 0 this is also. So, here you can all check the signs here, 0 flag, carry flag, parity flag and the overflow flag. You can check all of them, they will be consistent. Okay. So, this is our simulation output with respect to the description which we have given here, right, fine. So, it works correctly. Now, what we are trying to do here, we have just given a behavioral description of a full adder, of an adder. Now, this we want to refine into more detailed description. So, the first step what we do? The first step what we do is, we had started with the design of a 16-bit adder, right. So, what we are saying, we will be using 4-bit adders. Let us take 4 4-bit adders. So, they will be all fed with 2 4-bit numbers. They will be generating a sum. So, the carry in for the first stage will be 0 and this carry out will go into the carry in of this. This carry out will go into the carry in of this. This carry out will go into the carry in and this will be the final carry out. So, let us do a structural design like this. So, now we are implementing 16-bit adder using 4 bit adders and connecting them like this, ripple carry between the stages, right. So, this is our next step. So, well, this what you got, this with respect to the simulation output, we have also shown it here. Here I think there is a small typographical error, this should be s equal to 0. Okay. Fine, s equal to 0. See here s is 0 and it goes 1 here, it goes 1 here, last state. Okay. Fine. So, the waveform also you can see the same thing. So, this is x, this is y, sum is z, you can see the value 0 f f f, you can see the value 0 0 0 f f f f, you can see the values, right, and you can also see the flag value 0 or 1 whatever is coming. Fine. Okay. Now, in this second version, as I said, we are using 4-bit adders with ripple carry between blocks. Now, our this ALU description, module description, the first part remains the same. This was exactly identical with the previous one. What we have done? We have just added a wire. So, why we need this wire? We need this wire to just implement this intermediate carries. This we call as C1, this we call as C2, this we call as C2, C3, this intermediate carries. So, we are defining them as wires, okay? Wires C31, and we have just instantiated 4 adders like that. Okay. Just see exactly like that way. Here for the first adder, the inputs are x 0 to 3 and y 0 to 3. For the second adder, the inputs are x 4 to 7, 4 to 7, next one 8 to 11 and last one 12 to 15. Okay. So, for the first adder the carry in is 0, second adder carry in is C1, and for the first adder carry out is C1, for the second adder this C1 is the carry in. Here the carry out is C2, for the next adder C2 is the carry in, C3 is the carry out, for the next one C3 is the carry in, and the final carry out is carry. Okay. This is how the carry is generated, because here we have not shown the carry, carry will be generated like that, sign 0, parity and overflow are shown. Okay. Carry is coming here and these are the sum, but the 4-bit adder still we are leaving it in a behavioral description like this. This adder 4 is a 4-bit adder, this we are still defining like this. So, this design if you simulate, you will see that you are still getting the same simulation result, same simulation output. Okay. This you can verify, all right, fine. So, the next stage is that we are actually modeling these 4-bit adders as a ripple carry adder. See here in the earlier design we have just used this 4-bit adder modules, right. Now, what I am doing is that you see, you just look at this diagram, this 4-bit adder modules. So, each of these 4-bit adder modules we are expanding, we are using 4 full adders. We are using 4 full adders, and using 4 full adders we are using a ripple carry adder. So, the carry output of one will be going into the carry input of the next. These will be the inputs, okay, and some output. These are standard designs of adder. So, we are actually going for a ripple carry adder of 4 bits, which will be looking like this, 4 full adders in cascade. So, this is exactly what we have done. This adder for module, which earlier was looking like this behavioral, this we are making it structural now. We are implementing adder 4 by instantiating full adder 4 times and interconnecting them in a suitable way. Like the first one is getting A0 B0, C in is the carry in, C1 is here, C2 is here, C3 is here, and final carry out is C out. Okay. So, this version is also a very standard way. So, you see, if we have this refinement and if you do a simulation again, you will again see that you will be getting the same simulation result. So, I strongly suggest that you should actually go along with this class, not only listening to what I am saying, but also actually implementing and simulating the codes and seeing that whether it is working correctly or not. So, if you do this, you will see that still you will be getting the same result, which means that so far our design is correct. So far so good. Okay. Now, this full adders at the end, this full adders also you can implement using structural way, because you see this is one implementation of a full adder, which is a compact implementation which requires a total of 5 gates, 3 XOR gates, 2 AND gates. There are many implementations of a full adder, this is one possible implementation. So, here the structural implementation that I am showing here of full adder uses this netlist. So, you see this S, C out, A, B, C are the input and output lines, A, B, C is the input, S and C out are the output, and the intermediate wires are S1, C1 and C2. So, there are 3 XOR gates. So, we are instantiating the gates like this XOR G1 S1 AB, it means this is G1, S1 is the output, AB are the inputs. G2 S S1 C, this is G2 S S1 C. Last one G3 C out C through C1, C out G3 C out C2 C1, and there are 2 G4 C1 AB, this is G4 C1 A and B, G5 this is G5, C2 this is S1, this is C. So, you see when you instantiate gates in a structural way, you can group the similar gate types together, like the 3 XOR gates. Instead of writing XOR 3 times, I have written XOR once and just I have separated them by commas. This way you can write. So, you see now we have just arrived at a complete structural description of a 16-bit adder, where the individual 4-bit adders are also ripple carry. Now, let us also look at an improved version of this design, where this 4-bit adder that I have shown. So, instead of mapping this into a ripple carry adder like this, so we can map it as an alternative way into a carry lookahead adder. So, carry lookahead adder is a faster way to implement an adder. See, in a ripple carry adder, the carry is rippling through the stages. So, the worst case delay will be the maximum time it takes for the carry to ripple through. But in the carry lookahead adder, we are generating all the carries in parallel, so that the addition becomes very fast. So, in the next design, here we shall, or here we are looking at a design of a 4-bit adder, adder 4, using carry lookahead principle. Now, here let us skip this, we shall come back here. Before explaining this description, let us first look at how a carry lookahead adder works, okay? Because this will be required to understand how we have come up with these expressions, because these expressions may look a little complicated. Okay. So, you see for a ripple carry adder, means as we have seen, the total propagation delay will be proportional to the number of stages n, because as I said the carry ripples through from one stage to the other. So, carry lookahead adder is one way to speed up the addition, where the carry signals are generated in parallel for all the various stages. So, effectively the addition time reduces from order n in ripple carry adder to order 1, which is a constant time in carry lookahead adder. But the flip side is, the drawback is, the hardware complexity also increases very rapidly with the number of bits n. Okay. Let us see how. Well, if you look at a single full adder, so in a ripple carry adder you look at the ith stage full adder, where the inputs are a I, b I and c I, the output is a sum s I and a carry s I plus 1. Now, we are defining two signals or two, you can say two functions called carry generate and carry propagate. Well, carry generate specifies the condition where a carry is generated in the full adder irrespective of the carry in. The condition is, whenever both the data inputs a I and b I are 1, then carry will be generated irrespective of c I. So, that is g I, g I is a I and b I. And propagate, carry propagate represents the condition. It says that when the input carry will be propagating to the output, what is that condition? The condition is, means among a and b, at least one of them, means exactly one of them should be 1 and the other should be 0. Suppose it is 0 and 1, then if there is a carry coming 0, 1, 1, that will generate a carry, the carry will be propagating. So, this is the condition for carry propagation, exactly one of a I and b I should be 1. So, this carry propagation is defined by the exclusive OR function. This is generate and propagate. So, g I and p I you can implement by an AND gate and an XOR gate, right. Now, with this you can write that the output carry expression, output carry will be given by, well, either the carry is generated or the propagate condition is true and there is an input carry. So, c I plus 1 you can write down as by an expression g I or p I c I. Okay. Now, this you can use recursively to find out an expression, c I plus 1 equal to g I plus p I c I. So, you can write this c I, you can write as g I minus 1 plus p I minus 1 c I minus 1, you can expand it like this. This c I minus 1 again you can write as g I minus 2 plus p I minus 2 c I minus 2, like this you can recursively go on expanding. Okay. So, I am not showing you the whole thing. See, basically what it means, I am just writing down some simple expressions. See, what you got is c I plus 1 equal to g I plus p I c I. So, you can generate the carry for the first stage C 1 as you just substitute I equal to 0, g 0 plus p 0 c 0. So, what will be C 1? This C 1, C 2, C 2 will be, again you put g, you put I equal to 2 and I equal to 1. So, g 1 plus p 1 c 1, right. Now, C 1 you have already got this. So, you can substitute C 1 here. So, this becomes g 1 plus p 1 multiplied by this. So, p 1 g 0 plus p 1 p 0 c 0. You go to C 3, C 3 will be g 2 plus p 2 c 2. Now, C 2 you have already got this. So, this will be g 2 plus p 2 multiplied by this, multiply this, p 2 g 1 plus P 2 P 1 G 0 plus P 2 P 1 P 0 C 0 and so on, like this we will be getting the expression. So, you see all the carries you can get just by a 2 level AND OR kind of expression. There is no question of carries rippling through, but as you go on these expressions become more complex, bigger expressions, more number of gates. Okay? This is what I was saying. So, actually this is what I have just now showed. C 1 is this, C 2 is this, C 3 and C 4. So, you require so many gates and sum you can directly generate. You see P is nothing but A and B's XOR. So, this sum is the XOR of all the 3 bits. So, you can simply write P 0 XOR C 0. Similarly, S 1 is P 1 XOR C 1 and so on. You need 4 XOR gates. So, in a carry lookahead adder, in a carry lookahead, you have a circuit first which generates all the G and P's, which means XOR and AND gates. Then we have a carry lookahead circuit which implements these functions C 1, C 2, C 3, C 4 using AND OR circuits. So, it generates C 1, C 2, C 3 and also C 4. So, now you can directly generate the sums by using XORs, XOR the carry with the P's. So, the total time is constant irrespective of the number. Okay. There is no ripple of the carry. Okay. So, this will be much faster. So, just remember these expressions and the sum expressions. So, if you remember these expressions, you can just correlate that what you have done is exactly that. Here the carry propagate and generate signals I have defined as wires in between and the intermediate carries also. So, P 0 is A 0 XOR B 0, P 1 A 1 XOR B 1 and so on. Similarly, the generate signals and A 0 and B 0, A 1 and B 1 and so on. So, I generate the propagate signals, I generate the carry generate signals, then I generate all the carry signals C 1 equal to G 0 or P 0 C in. C in is C 0. You see this expression C 1 equal to G 0 or P 0, this C 0 is C in, C 2 is G 1 P 1 G 0, P 1 P 0 C in. Exactly we have written down that expression C 2 equal to G 1 or P 1 G 0 or P 1 P 0 C in, C 3 and C 4 is finally C out. So, as you can see, as the number of bits increases, these expressions are becoming more complicated and finally, sum is the XORs. So, this is a carry lookahead adder. So, in the same way as I said, you can replace a module by a better or an improved module. You replace a module by another module, like for example, we replaced a 4-bit carry lookahead adder by a 4-bit ripple carry adder by a 4-bit carry lookahead adder. We have got a faster adder, but we can do simulation and you can find out that functionally our design is correct, it is working correctly. So, this actually completes our discussion for today's lecture. See, what I tried to illustrate over the last 2 examples we discussed is that when we look at non-trivial designs, slightly bigger designs, we often break the design up in a hierarchical fashion. Whatever something was discussed in a or described in a behavioral fashion at one level, we do some kind of iterative refinement. We break that behavioral description into structural description, try to be more detailed, and we repeat the process until we reach a point where our entire design becomes structural. So, in a normal digital system design, you will see later that we do not only have combination circuits, we also have sequential circuits, flip flops, state machines and so on. So, we shall see later that when we have such a system where we have combination circuits, registers and also lot of finite state machines, there it may not be worthwhile to convert all the modules, all the descriptions into structural. Well, the data path, the circuits where the actual calculations or computations are carried out, those of course, we can convert into structural fashion, but the controller, the circuit which implements a finite state machine which generates the control signals, often that we do not convert into a structural fashion, because it involves too much of a work on the part of the designer. So, we shall just learn these things slowly over the next lectures. Thank you.